what I thought we'd talk about today is a bit about fitting and a bit about Fourier transforms. So there are kind of two things that are related and two things that are not uncommon in scientific computing again. The fitting is really here so that you know that it is possible. It's also just a routine in GSL, so we can go over it fairly quickly. But it leads to things like frequency analysis, which leads to Fourier transforms and application. Who here has not heard of a Fourier transform? Excellent. That's how it should be. You all know what it is. So this is going to be. We can focus on the things that are different in a numerical sense, most and foremost. Okay, so fitting. You have some data. You want to fit it. What are you going to do? So I wanted this one to be fairly explicit. So here's a way to generate some data. Doesn't really matter what the details are, but I have two arrays essentially, or one x values, one y values, and I've given it some random noise. I'm going a little bit ahead here and saying there is a nice random number facility in C++11. So we'll see that again next class, but we're using it here again just to add some noise to this. And then I'm writing this out to a file or to standard out. And so suppose that I've created that data and I've put it in an array. Let's say, then how do I fit it? Well, I just use a routine from the GSL. In this case, there's a linear fit. I give it the two arrays, x values, y values, how big it is. And then covariant matrices will have to be filled. And since the GSL is a C library, everything is going to go through pointers. So there's these ampersands so that these things can be filled. But in other words, this is the way you pass it by reference in a C kind of fashion. So once it's done, we can get back what the y values are, again from a GSL call. So it's kind of abstract. It gets a little verbose because everything has to be going through the GSL. You could get the coefficients out yourself as well and just compute the linear fit, but there's a routine for it too. And then you get your fit. So that's one of the things that is also in there, and it's of course not the only thing. So we made some data. We are trying to do a linear fit, so we just give it to the routine. But it's always good to know when you're doing data fitting what this routine is really doing. Once you're fitting or once you're doing any kind of statistics, there's a bit of magic involved, right? So it's good to know that what we're really doing when we're doing this linear fit is assuming that the error is Gaussian distributed, independent between the samples, and that we're going to minimize the difference between the line and the point. So if we go back to the points, we take the differences of each point and the proposed line, we square it because we don't want the negative ones to cancel the positive ones, and then we say, well, what's the minimum? You can argue that this also maximizes the likelihood that these are your correct parameters. So that's another way to see it. So you make the least squares. So these are ordinary least squares, and this is what this routine does. You could see cases where this would not work. If you know that your errors aren't Gaussian at all, or if you know that your data is somehow correlated point by point, you should be worried, right? You should be doing something else. Don't just trust it blindly. So what else could we do? And I think all the things that I've listed here are available in the GSL. I could take. I had error estimates only in y. I can get them in x as well. I could have several values of x and y here. I had one-dimensional parameter. You can have multiple parameters. And this kind of least square stuff really generalizes nicely, not just to things that are linear, but things that are of any form, as long as the parameters are linear. So this case here, we have a linear form in a and b, as well as in the independent variable x. The only thing that matters for this to work is that a and b occur linearly. The x could be x squared, could be x cubed. The same kind of least square stuff would work, because we're really minimizing with respect to a and b. So that's the linearity that matters. Okay. If you have nonlinear forms, there's something else you can do. But now, basically, you're solving a nonlinear equation. So whenever you find yourself in nonlinear parameters forms, even if there's a routine for it, it means it's actually doing root finding, the thing that we did last time. One thing to worry about a little bit with least squares is it can be sensitive to outliers. So if you have data that is really, there could be some points that are really just errors, right? Measurement errors. If you want to use least squares, you might have to come up with a way to justify that you leave them out. But there are other methods, other sort of cost functions. They don't care so much about them. So I won't go into that, but this is just something to be aware of when you're doing fitting. Oh, if you want to seem fancy, you just call all your fitting machine learning. Okay, that's true. It's part of machine learning. You just taught the machine how to plot, or not to plot, to fit. Anyway, and finally, even if you're doing this least square algorithm, what you get, just to tie this all together, is the following. So you assume that you have a form that is linear in your parameters. Parameters here are the beta j, and then these are essentially basis functions. So this was just x before. Fj was just x, but it could have x squared. I could have a whole set of possible forms that I want to fit at. And by minimizing essentially the squares of the difference between the data and the proposed theoretical estimate, what we really have, if we view this fjxi as a matrix, we have a matrix equation to solve for beta. This should have been beta. So this is exactly an ax equals b. So in the case of least squares, essentially what we're doing is just linear algebra. And in fact, the GSL the libraries or functions will use the BLAST routines under the hood to solve this stuff. And we've actually seen this already. If you recall, there might have been that the F matrix was called an A matrix before, but we saw essentially how you solve overdetermined set of equations, and that gave you the same answer. So this is another way to look at this. So fitting in the least square case gives you linear algebra. In the nonlinear parameter case, it gives you root finding. And now all of that is already taken care of in the GSL, right? So you don't have to recode that, but that is what's happening. Yeah. Yes. So if you have an error that varies, then what happens essentially to make this work? If you know that the error is different, so basically what you're asking is, what if the error is not independent, right? Because if all the errors are the same, then it doesn't really matter. But if I have an error associated with each point, I can essentially weigh each I vector differently. Right. So the uncertainty here comes from assuming that there is a Gaussian distribution. So you saw that the routine actually returns you an error for this point. Oh, for each parameter, I see what you mean. I think those are, good question. Let's see, so this gives me the covariant, and this gives me y and the area in it. Yeah, so that is encoded in some of these, but I forgot exactly what you would. Yeah, it's there somewhere. I'd have to look at the actual routine and its documentation to see that. But yeah, I think you could. The thing is, it doesn't really say. You might need. I think you can't absolutely say this because you don't know. Let's look at the model again. Where's the model? Here. If we don't know the sort of the strength, the size of this error per se, then we can't really say what the error in A and B are. But once we sort of assign that some sort of value, we can. But we can give a scale. We can say, okay, am I very certain in this B or this A or not? Is it likely that they are true? But it kind of depends on what I assume my errors to be. Right? Yeah. Anyway, that's statistics. So this isn't the statistics class, but those statistical routines are there for you. And I just really want to say be careful that you know what it's really doing, even though there is a routine that does it. Now, from just mere fitting, we could try and do that too if we wanted to do, say, frequency analysis. We have some signal. We're imagining that it's basically a bunch of sines and cosines together, and we want to know what kind of frequencies are in there. We could just say, well, let's make a guess for what our signal would look like with some strength parameters per frequency omega, so B1, B2. And then this is of a linear form, so we just give that to our least squares routine, and we find out what the B1 and B2s are, and what are our dominant frequencies. We could do that. But if you do that, you're going to get ridiculous oscillations in your data. And there's actually a better way to do this. You can imagine that if you have even a small component of a high frequency one, you suddenly get lots of wiggles in your signal. So the better way to do it is to do a Fourier transform. And because this is numerics, it's going to be a discrete Fourier transform. So here's Mr. Fourier. We're going to look at a library that does Fourier transforms for us called FFTW. So let me give you a function that kind of is awkward to see, but it's this cusp function, which I think is 1 over something. You could imagine having that function as a variable of x and then transform in Fourier space. And since you've all told me that you know what a Fourier transform is, you would remember that this is kind of what it looks like. I'm presenting the complex case because it's actually the easiest case to explain. You have a complex phase vector that you multiply your function with, depends on a k vector. In general, this is a vector if x is a vector, and you get a signal. So you get a signal. So I had a signal in physical space, a spatial signal, and I changed it into a Fourier space, which k lives, and that could look something like this. In this case, the two look kind of similar, although the Fourier space is smooth. Okay, spatial wave vectors. You can call wave vectors, you can call it frequencies. If this is time, then these are frequencies. If this is space, these are wave vectors. Those are the two spaces. You can go back and forth, so that's kind of nice. So what Fourier did, and why I have his picture up there, is that he showed that you can have any function expressed in a series of harmonic functions. In other words, there's a Fourier transform for any function. There is some caveats on what the functions mathematically have to be, but fine. So the Fourier transform is really saying, I have a function, I can express it as a sum of sines and cosines, or complex phase vectors. Now, once you know that, and you're looking at it again, really what you're doing is you're taking your signal, represent it as the points in space, and re-represent it as coefficients of the Fourier basis. So it's really just a transformation, a basis transformation in function space. Now we're not going to do much with that, but it isn't as mysterious as that. It's just basically you're doing another matrix multiplication on your signal. So you go from spatial to wave vector or time to frequency, whatever you want to, whatever is applicable to your case. And then something that will be a nuisance as you're applying this is that you have to worry about constants and signs, but all of them are conventions. So I'm not going to worry too much about it here. It's something that you have to worry about. So when I'm writing this proportionality, I'm doing that because, well, I don't really want to worry about what my normalization here is, because there's different conventions. It depends on your field, it depends on your numerical library. Similarly, whether the plus sign here or the minus sign here is taken, it's a matter of conventions, what you call x or minus x. So that's what I mean with they're just conventions. They have to be, there's some restrictions, but they're conventions. So let's look at the discrete Fourier transform. We are rarely given a signal with an infinite number of points, and even if we are, computers wouldn't help us with it. So we have usually a discrete point of view in numerics. And so one of the more common ways of getting a discrete signal is taking a function and only evaluate it at fixed intervals, so fixed intervals delta x, and calling that essentially an array of n numbers. So f could be a function, but fj is just a set of numbers. And that is a way more common way in which we get data, right? Unless you're doing math or theory, this is how you get your data. And this too can be Fourier transformed, and the form is a little bit different. We don't have an integral, we have a summation. We still have our phase factors, and by convention, this is how they look. So you have your 2 pi I here. J was your index here, so it's an integer, and k again is an integer. That's how far along we are in the Fourier array. So if my say spatial array and my Fourier array, or my time array and my frequency array, but they're all indexed as integers. So j here is an integer that corresponds to a physical position of j times delta x. And likewise, k here is just an integer that indicates what number of the wave of frequency I'm looking at. Now again, you can transform that back quite easily by reversing the sign. So although the signs are a convention, if you want to go invert this matrix or this transform, you have to switch the sign. And then to make things truly an inverse, in the sense that if I did transformation to the headed and then back to the unheaded and get the same thing, that's what an inverse should mean, I have to do this 1 over n. It's easy to convince yourself that that's the case. So there are, so conventions mean that I could have put something in here and then something else should have been in front of here. I'm sticking with this one for now, but it doesn't matter. Okay. So I can go back and forth quite easily just by doing a little summation. Oh, this was supposed to be LaTeX. So let's look at this one more time. That's odd that happened. The k vector here and the j vector here, they're basically a bunch of numbers, right? That's in total n numbers. So this is a vector and this is a vector. That means I can see this as a matrix multiplication, where the matrix elements, the jk elements are this, and then I'm just multiplying it as a matrix vector multiplication. So you'd say, well, great, we're back to linear algebra again. I'm glad we took 3 lectures to do that because we're using it so often. So it is a linear transformation, and therefore it is a matrix vector multiplication. But what is a little bit annoying is that for that, I think there's actually n to the third, it's kind of costly to do that matrix multiplication. Now, if that's all we can do, then so be it. We'll just do it, and we'll use our optimized BLAS routines to do it. But it turns out that we don't have to do that. So here's my non-optimized version as a comparison. I'm taking a complex array and giving f hat back. I'm just doing a double loop. I'm not even constructing the matrix. I'm just doing it by explicit manipulation. So even when Gauss came up with this discrete Fourier transform, he was one of the first that tried this or even came up with the idea. As soon as they came up with the idea, he realized that this idea, the straightforward way of computing this, is just too slow. Gauss was a very clever guy, and so he said, well, of course you can do that, but I'm not even going to pretend that that's what you do. What you do is a fast Fourier transform. So he came up with this fast Fourier transform way of computing this in n log n operations rather than something of the order of n squared. Now, he did this, he wrote it down, but he wrote it in a little note, and people forgot. And although it was published in his diary, they forgot, and it had to be rediscovered in 1965 in the slightly modified form. So it's kind of funny that as soon as people did discrete Fourier transform, the first guy that did it came up with a fast Fourier transform as well, but then subsequently we all forgot about it. Now we know about it again. It's been a while, so that's good. And the basic idea is kind of funny. It uses in a sense, it uses a special structure that this matrix multiplication has. The matrix is kind of special. So all these phase vectors. It'll allow you to write any n-point fast Fourier transform as a sum of 2 n over 2 points transforms. And if you repeat this recursively until you only have 1 point to to deal with, you've taken log n steps. Okay, so essentially, because each level would still have n computations, you get n log n. Now, here I'm cutting things up in 2 parts, and we'll see how it goes. I could do it in 3 parts, 5 parts, 7 parts. Any odd number kind of works, or a non-divisible number anyway. And in case you're not too concerned about the n log n versus n squared, here's a few matrix sizes, and here's the speed up you would get from doing this. And so even if you have a fairly modest 100 by 100 matrix, you get about 18 times faster performance. This really it doesn't seem like a big difference. There is a big difference. So it's worth using fast Fourier transforms. Just because I know some of you are curious, how does it work? So you take your original Fourier transform, but you write it a little bit differently. This omega is going to be sort of the basic frequency. It's the smallest frequency that's in there, smallest frequency phase factor. So it's e to the 2i over n. It's some small phase factor. We'll call it omega. And it depends on the size of your problem. So that's why the n is there. And then you can quickly show that you can write the whole transformation as multiplications of powers of this omega. And so it's the fact that these powers are now related. They all have the same base, that you can do something like this. You can take your Fourier transform and write it as a sum of the even and the odd samples, and that gives you essentially an omega n over 2 here. This is a Fourier transform just of the even samples, and this is the Fourier transform of the odd samples. So I'm dividing my samples up, even and odd. I take the Fourier transforms and then I add them with a little bit of a prefactor here, but that's just one prefactor. And then I'll do that again and again and again. Now, that gives you this n log n. This is great, but you can imagine that keeping track of all the even and odd samples, and then the next step, all of the things that are divisible by 4, or divisible by 4 with the remainder of 1, or divisible by 4 with the remainder of 2, divisible by 4. That is some bookkeeping, because you have to basically create subset of these all over the place. So there's some shuffling around of data to make sure that this happens. You don't really want to be bothered with that. This is what happens for you, but essentially you want to go to a routine that does that for you. So of course it's been already done. This is our library section, right? This is don't code it yourself. You're better than that. Somebody else has already done this, and so one of the guys that have done this are the guys that have coded in the fast Fourier transform, the fastest Fourier transform in the West. It's a little cheeky. I hear they're allowed to use it in Europe too, so it's not necessarily just the West. Even in the East, they're allowed to use it, and it's still pretty fast. But there's a couple of, so you want to use libraries, and I'm using FFTW because it's open source, it's free, but it's not the only player. The Intel guys make the Intel math kernel library that has the Fourier transform. The IBM guys make something scientific library, ESSL, and they make them tuned for their hardware, and they tend to be a little bit faster. Okay, so these guys, you would have to pay for it, or you use a system like Cynet that has paid for it for you, and you get a little bit better performance typically. But that's tweaking that last bit of optimization. This is still scaling the same way, and it's pretty fast. Okay. One of the nice things that we'll see that it does is it has a way of selecting from different possible ways of optimizing the ones that's best for your computer, and so that's how it can be sort of the fastest, faster than previous ones anyway. Okay, so it's really hard to do this well yourself. Don't try it. These guys have solved it for you. You have better things to do. So here's a little example of how you would do it with FFTW. So it's the same idea. You have a complex vector coming in, complex array coming in, complex array coming out. I think the other one had it too. You can either go forward or backwards in this case. You create a plan. You give it the arrays you want to work on, whether you want to go forward or backwards, and then you execute your plan and you destroy the plan. That seems a little bit elaborate for just one Fourier transform. to have 3 steps. But you can save these plans. So the plans are where FFTW decides what is the best way to do this. There might be a better way to do small matrices than big matrices. Big matrices might have to be chopped up in some way, or big vectors. There might be things that you can do. So as it makes the plans, it tries to estimate the best way to proceed, and then you could execute it several times. And so there are cases where you have to go back and forth between real space and Fourier space, between frequency and time domain. And if you have to go back and forth a lot acting on the same arrays, having the plan estimate its best way of proceeding once and then execute again and again is a good way to go about. So the fact that this is separated out can be helpful. So the inverse is the same way. So for the FFTW, it's just a different flag. But something to mention that I should mention here, and why there's even a whole slide on it, is that although this is the inverse, virtually all of the implementations of the fast Fourier transform forget about the 1 over n. So you take the transform, you give it, and you let FFTW compute the transform, you let it compute the inverse transform, and you don't get the same thing back. You get the same thing back multiplied by n, where n is the length of your vector. So if you care about that, you'll have to divide by n yourself. It's a small thing. You can imagine that it's actually easier to just flip the switch for the implementation and do nothing else to get the inverse than to also compute this. Okay. We can go back and forth very quickly between x and k, or time and frequency. And so sometimes you have a part of the computation that is easier done in Fourier space, and sometimes, but another part that's easier done, say, in regular space, and going back and forth is quite common. Now, there's a few things that I want to warn you about, and I'm going to do them on the hand of this, or by looking at this example. It's a simple example. It's a 1D signal. The signal it's a rectangle function. So I don't know why the plot is not as weird, but imagine that there's a function that is, so the initial function that you put in is the sinc function, so sine x over x, kind of a wiggly function with a peak in the middle. Okay, take a couple of points, forwards, transforms, and by using FFTW, the true Fourier transform of the signal is the rectangle function. So only wave vectors that are less than 1 have a contribution, and or wave numbers that have a value less than 1 have a contribution, and all of us are 0. Okay. So I'm going to do that to see if it matches. So here's my creation of the forward and backwards solutions. There's no, I don't want to have any secrets here. I'm really just computing these things with Fourier transforms. Okay. So sync ffTw.cc is the name of that code. Creates it. I write it out to output. For some reason, I have to do this trick. And then I'm using Python to plot it, just so that you can do it yourself. So here's our signal. This is the sync function. And there's a few, and here's its Fourier transform. So let's look at the left part first. You'll notice that the actual value of the x-axis is kind of funny. This is just a sample number. This is what I said. The only thing that's really kept is the index in the array. The actual x value isn't kept here. So to really interpret this, I would have to multiply this with the delta x that I showed and look up what it was. But and so you'll see that the actual signals should be peaked at 0, but here 0 is sort of in the middle of the sample. Oh well. But the Fourier transform doesn't look like a rectangle at all. It looks like an H. And it only looks like the H because if you look carefully, there is a blue line here. And this one is more clear. Okay. So if you see this for the first time, you should think that the fast Fourier transform is not working, because it's not giving me a rectangle, and I know show it analytically this is going to be a rectangle if I Fourier transform it. What went wrong? So one of the things to keep in mind is that when we make things discrete, what we and on a finite domain, what we're doing is essentially making them have periodic boundary conditions. So anytime you have so in this domain, let's look here first. That's not so it means that I'm taking this thing as a periodic function. That's not strange. These are all periodic functions, right? They're oscillations. They're all periodic. So this continues, as it were, in the back on the left side here, and keeps on going forever. Think of it that way. You keep on going forever. And so the point here is equivalent to going around once. Something similar is happening here. So because of the periodic boundary conditions, these are all positive numbers. The negative frequencies are actually stored at the highest frequencies. There's an equivalence of high frequencies and negative frequencies. So if I wrap things around, if I take that h function and rather than plotting it just like that, I'd say, well, let's take everything that's on the far ends and glue it on the front end, I actually get this signal. So the x-axis is gone. But this is 0. These are negative frequencies and positive frequencies. I had no negative frequencies. I had to do this wraparound of n minus k. This is closer to what I might want, but it still oscillates like crazy. And the reason it oscillates like crazy is, which I can undo. So I artificially undid this by multiplying every other number by -1, and now I get a rectangle. So I had to do two things. I had to wrap things around, and I had to multiply by an alternating sign to get the right answer. This still should tell you something's fishy with the Fourier transform. We've talked about this already. So what we're using here is that, or what we have to use is this idea that there's an equivalence of k minus 1 and k. I have to go back. Yes. So here. So any negative wave vector is found all the way at the end. Okay. So if I have a sample of in this case, what was it, 16,000 points, then wave vector -1 is at 16,000 minus 1. It's right over here. So that's point 1. But the second point is that even if I've done this, I get this weird oscillation. And this oscillation is actually due to the fact that this guy is not symmetric around 0. So our real function would become a rectangle if it's around 0, but this is shifted. And it's shifted around half the size of the interval. Guess what the phase vector is associated with shifting over half an interval? It's -1. So every other point gets multiplied by -1. You would normally care about putting this on the other side. You would not care too much about these wiggles. They are actually not going to hurt you. It will disappear when you transform back. But if you want to interpret this as an actual signal, you want to know what frequencies are in there, you'd actually cut off, you would do this wraparound so that you can identify negative signals. Yeah? Yes, so this width, so I've zoomed in here, okay, which is unfortunate because the x-axis is gone. But yeah, this is zoomed in, because if it didn't, we would now see a cross. Yes. If I zoomed in on this side, I would see wiggly lines. Yes. So in this case, I'm plotting the real part. So this is a real signal. That means that this has some extra symmetries, but I'm plotting just the real part in this case. According to the theory here, this signal should come out to be completely real. If it's symmetric, exactly. But because it's shifted, as far as the index is concerned, there'll actually be some. So talking about real signals, which is often something you have additional symmetries in your Fourier transform. So whenever you have a real signal, so this expresses that the complex conjugate of your signal is its signal itself. Doesn't give you a real signal back in the Fourier space, but rather gives you a symmetry where the kth number is the n minus kth number complex conjugate. So this means that you still are storing, you would be storing too much information, right? Because you have to pass in a complex array where the imaginary parts are 0, and you get back a complex array in which some half of the numbers can be basically determined from the first half. So in terms of storage, if you did it that way, if you're using just the complex numbers to store a real signal and then get the Fourier transform back, you're essentially storing twice as much information than you need. You can use these symmetries either like this on the time domain or here on the frequency domain. You can use these to store only half of the stuff and sort of reconstruct the rest. But you can imagine there's different ways of doing that. You could say, well, for this guy, I'm just storing the real parts. That would make sense. But then in this guy, what am I doing? Am I going to store just half, or am I going to store the whole thing but leave out or store first the real part and then store some imaginary parts? Like, there's different ways I can store real parts, imaginary parts. So different storage choices can be made and are made whenever you try to do this. So if you want to really deal with real data, you're going to have to look at, okay, what kind of routines are there in there to deal with real data in your library, and how do I get them out? This becomes a little bit in one dimension. It's not such a big deal. It's easy in the sense that you read the documentation. Okay, the signal that I'm really after is encoded in a certain way, is stored in a certain way. That's fine. Okay. So you could store in what's called a half-complex storage, where the first n/2 are the real parts and the average part in reverse order. There's advantages to different storage patterns. Essentially, you're going to read the document and say, okay, this is how I get my signal back. If you only deal with complex data, as I said, the complex case is the easy case in this case. There's nothing superfluous. There's no loss in storage because you have to store everything. But for real data, this is something to be worried about. Now, if you think this is tricky, in the higher dimension becomes even trickier. Not in theory. In theory, it's very simple. So multidimensional transforms just have two indices. So you basically have a matrix, and the matrix gets transformed. It's something that looks very, very similar. You have your negative frequencies, again, in a shifted way. Not a big deal. And there's routines for that for 2 and 3 dimensions in the fast Fourier transform. So that's easy. You want to use this because you want to be careful. You could apply it to each dimension and then transpose. Let the libraries deal with how to do this. Okay, there's different strategies to do. You'd still get n log n, and you don't forget about it. But it's harder. It's more work to get these to perform, and so it's definitely a case where you want to depend on libraries to do it. Again, the real case, like transforming real data and getting all the bits and pieces in the right spot again is even harder. So I want to end with a few applications of this, maybe just one. So when do you need the Fourier transform? Well, you'll need it certainly when you're doing signal processing and you want to know about the frequency components. But it also turns out that a lot of equations can be solved more easily using Fourier transforms. And the reason is that this little phase vector here happens to be what's called an eigenfunction of the differential operator, which means that you can turn partial differential equations, which we've covered a few weeks back, into ordinary differential equations, which you have also covered and which were a little easier to deal with. And in the process, you could actually avoid some of the matrix multiplications. Okay, so let me give you an example. Here's our old heat equation. We saw this when we did the PDEs. The gradient squared times some parameter, which I'm calling alpha. A few lectures back, it was called k, but k will be a wave vector here. So suppose we Fourier transform this, and we do this exactly. What this little double gradient turns into is just the square of the wave number, and there's a minus sign because it's actually I squared. This is not a partial differential equation. It's an ordinary differential equation. So we could just discrete time in this one and solve the equation and keep things very simple. In this case, it's even simpler because we can actually solve this exactly. So by using a Fourier transform, we could solve the heat equation by exactly by just doing it. There's nothing to do. So that's solving the time evolution. It's almost trivial. Of course, in a real application, you'll probably be given some initial heat profile, some T0, which you then have to transform into a Fourier transform. Then you apply this and you Fourier transform back. You might have to worry about things like boundary conditions, which I haven't touched upon here, which also live in physical space. So there is still, even in this case, where the application is almost direct of a Fourier transform, there's a component that is easiest done in real space, such as suppose you had boundary conditions at the beginning of the interval, it's one temperature, the other side is another temperature. You can impose that in the spatial representation easily. You just set the value to whatever value it needs to be. Whereas in Fourier space, this becomes complicated. So you set it in real space, you do your Fourier transform, you apply this, and you Fourier transform back. Okay. Yes. And that's the simpler case. So even here we have this interplay between spatial and wave vector space. There are cases where you go back and forth more frequently, where there might be something that happens on a localized level. I know I'm thinking of maybe there's some variation in the parameter alpha depending on where you are. Well, that will be easier to do in real space. Another thing that I want to mention, because it seems very trivial, is that this solution is different from the solution that we get when we do a discretized space. So when we discretize space in the PDE level, we got a matrix out. We had this tridiagonal form. It was nice. We could solve it. It wasn't a big deal. We used BLAS or laid back for it. That is a different solution than this. And there's good things and bad things, but if you just wanted to compare the two, you would see that that they're not the same. And they're not the same because I haven't discretized space here. So in essence, I've taken an infinite discretization. That sounds great, but it means that I can't compare the two. If I wanted to compare the two, what turns out to be the case is that there's actually something different going on. This k squared is not really true anymore. And I'm mentioning this because you could imagine some odd things happening here if I want to include negative k values. So the negative k values were equal to the large k values in the discrete case. Remember that? So which one of the two would I choose here? Because it matters. Taking -1 or taking n-1 here really changes what my signal is. So I kind of have to interpret this in some sort of way. Now then, you have to use your physics sense again and say, okay, what I mean probably is sort of the smallest k that is associated with this. And why does it not really matter? Well, it doesn't really matter because all the large k values are highly damped. So this approximation of saying, oh, I'm just taking the infinite limit approach only works if you do it in the right way. This k value in this case should be the one that's sort of closest to 0. But if it wasn't highly damped, if something else was going on, I'd have to be more careful. I'd have to be more careful using this and thinking that I'm really solving it. Okay. Okay. So lots of little points in using discrete Fourier transforms that I hope I at least warned you about. We'll likely have some chance to play with this, and you'll see how it goes. Questions? All right. Good.